This video is going to look at section 1.12 Acids and Bases of the AQA A-Level Chemistry course, specifically looking at the pH of strong bases and Kw. The video is going to cover a recap of Ka, the pH of pure water, Kw expressions, calculating the pH of strong bases, and calculations involving reactions of strong bases. Now for this video, it's really important that you ensure you've got a sound understanding of the basics of pH calculations, including calculating the pH of strong acids, as well as the use of Ka expressions. So go back and have a watch of the video on weak acids and Ka if you do need a recap. To start off with, I want you to have a think. What would the pH be of a 0.1 mole per decimeter cubed solution of NaOH? Maybe have a pause of the video and see if you can come up with an answer. So if we were to have a quick go at this, we might think to ourselves, right, NaOH, that's a strong base. So that's going to fully dissociate. And you might think, okay, the concentration of 0.1 mole per decimeter cubed, well, that's going to be the concentration of the NaOH. So you might think to yourself, pH is minus log to the base 10 of the concentration of H plus aqueous. And putting that into your calculator, minus log to the base 10 of 0.1 gives us a pH of 1. But there are a couple of issues with that, which you may have noticed when you attempted the question. First of all, pH is using concentration of H+, and NaOH would actually give us the concentration of OH-, which is what is 0.1 in this. The other thing is that we've got a pH of 1. Now that would be an acidic pH. A pH of 1 isn't a sensible pH answer for a solution of a strong base. We'd be looking at something sort of between 13 and 14. So we can't go straight into using pH equals minus log to the base 10 H plus to work out pH of strong bases in a very similar way to the fact that we can't do that for weak acids. So like with weak acids, where we have to have another expression, Ka, to be able to calculate the pH of weak acids, for bases or strong bases particularly, it's a similar situation. We need another expression, and we're going to work through what that expression is. To get to the expression, we're going to start off looking at water. So, what would the concentration of H plus be in pure water at standard conditions? Have a quick think about what you know about pure water and what you know about pH in this topic to see if you can have a think about what that concentration of H plus might be in pure water. Well, to give you a hint, the first thing we know about pure water is that it has a pH of 7 at standard conditions. And we should know now that pH is minus log to the base 10 of H plus aqueous. And that we can use the inverse of that to calculate the concentration of the H plus aqueous, which is what this question is asking us to do, the concentration of H plus. So if we do 10 to the minus pH, or 10 to the minus 7, we get an answer for the concentration of H plus of 1 times 10 to the minus 7 moles per decimeter cubed at standard conditions. And that is 100% correct. That is the concentration of hydrogen ions in pure water at standard conditions. Now, it might seem strange that we've got a concentration of H plus in pure water, which you would imagine would be just H2O, but even in pure water, there will be a degree of dissociation. A tiny number of the water molecules will break into H plus and OH minus due to the amphoteric nature of water molecules. Now remember that amphoteric means behaves as both acid and base. So what water can do is if we take a water molecule, it can donate an H plus to another water molecule to form the hydroxonium ion and hydroxide ion. Now, to make this a little bit more scientific, okay, I'm going to use a reversible arrow because this is an equilibrium that sets up, and I'm going to put the state symbols in. And that is the equilibrium that we get set up. Now we can just look at one water molecule and look at what happens to it. And it follows a standard dissociation pattern that we've seen with weak acids. And so we can write an equation just for the dissociation of one water molecule. But in each case they are in equilibrium, and it can shift left and right. So have a think. What would happen to the pH if we increased the temperature of the water? So would the pH go up or down when we increase the temperature? And again, we are thinking about this equilibrium. Now what we're doing here is we're breaking bonds. And at higher temperatures, more bonds will break. Now if we think about why that is, breaking bonds is an endothermic process. So as we go left to right, this is endothermic. Energy is taken in to break bonds. Now, if we think about Le Chatelier's principle, if we increase the temperature, the reaction will oppose that change and it will decrease the temperature. And it will actually favour the forwards reaction because that will take energy in and decrease the temperature back down again. So at higher temperatures, more bonds will break and therefore the concentration of H+ increases. The equilibrium shifts to the right, favouring the production of H+. Now, as the pH scale is an inverse scale, as concentration of H+ increases, pH will decrease. Now, what's really important to recognise here is the fact that neutral does not mean pH 7. Pure water is always neutral. But if we think about pH decreasing or increasing when we change temperature, and actually I can give you a little fact here, that at 0 degrees C, the pH of water actually equals 7.47. So at higher temperatures, we get more acidic water, and at lower temperatures, we get more alkaline water. But water is always considered to be neutral when it is pure. And this leads us to this fact of neutral does not equal pH 7. That's not the definition of something being neutral. The definition of neutral is that the concentration of H+ equals the concentration of OH-. And that is always going to be true for pure water. So pure water is always neutral, and that's because one water molecule breaks apart into one H+ and one OH-, and therefore you're always going to have the same number of H+ and OH-, and the concentrations will be equal. So moving on to some expressions for water, which is what's going to allow us to be able to calculate strong base pH. We're going to do similar with water as what we did for weak acids. So what would the expression for Kc be for the dissociation of water? And there's the equilibrium again. Well, this will actually be the Ka as well. The Kc and the Ka for this will be exactly the same. And Kc will be equal to the concentration of the products times by each other divided by the concentration of the reactants. So there's the Kc expression, which, as I said, is actually the same as the Ka for this one. Now, when we looked at Ka, we worked out the Ka expression by taking the Kc and thinking about the ratio between the amount of water present in the solution and the actual ions that we're interested in. Now, the same thing occurs here. In a solution of pure water, there is going to be vastly more H2O molecules than there will be H+ and OH-. The degree of dissociation is tiny. So because the concentration of water is so high compared to the degree of ionization, we can consider it constant. Now, in science, in maths, if something is constant, we can neglect it. We can take it out of an expression. And this gives us a new expression. So neglecting concentration of H2O due to this gives us a new expression known as the ionic product of water, kW. And if we cancel out the H2O, in this calculation, in this expression, we get Kw is equal to the concentration of H plus times the concentration of OH minus. And that is the expression for Kw. Now that is always the expression for Kw. It doesn't change because it's based on water. So that is always the same and must be learnt. Now, ionic product of water, well, we're actually taking the products of the ionization, so that's one way to remember it, but we're also timesing together, and product also is a way of saying multiply. So we're multiplying the ionic products of water as well, because we would be putting a times in between here. So looking at Kw in a bit more detail, Kw is a constant. As I said, that expression does not change, and we can take the value to be a constant as well. Now, if the pH of pure water at standard conditions is 7, as we've said already, with a corresponding concentration of 1 times 10 to the minus 7 for H+, as we worked out before, that enables us to calculate the value of Kw. Now, as I've already said, in pure water, the concentration of H+ will be equal to the concentration of OH-, because one molecule splits into one H+ and one OH-. And we always will have the same number of H+ and OH- present in a sample of pure water. Now, because of that, we can simplify the Kw expression, just for this purpose of working out the value, to be concentration of H+ squared, because of OH- being equal to H+. Now, we know the concentration of H+ in pure water at standard conditions is 1 times 10 to the minus 7. So if we square that, that will give us the value of Kw, which is 1 times 10 to the minus 14. Now, because we're doing concentration times concentration here, or concentration squared, we end up with units of moles squared dm minus 6. Now, as I said, that is a constant. That is the value of Kw at standard conditions, and that does not change as long as standard conditions are kept. So when acids or bases are added to water, the value of Kw remains the same. As we just said, it's a constant. But the concentrations of H+ and OH- will change. And we can use this Kw expression to calculate the corresponding values of H+ and OH-. Now, when we add sodium hydroxide to water, for example, the OH- is present in the sodium hydroxide will cause more waters to break apart and will change the numbers of H+ and OH- in the water. And that's what we can do with Kw, is to work out by how much it changes. So, to look at an example, what is the pH of a 0.1 mole per decimeter cubed solution of NaOH? The question that we started with at the beginning. Now, we said it wasn't pH 1, that would be incorrect, but we can use Kw to calculate this. So it's really, really important to think like a chemist when you do these calculations, and to think through, what do we know about the information we've been given? So first of all, they're saying, what is the pH of this solution of sodium hydroxide? Now, we know that pH is equal to minus log to the base 10 of the concentration of H+. So we're going to need H+ to be able to work out pH. But we've got NaOH, and we've got a concentration here of NaOH. Now, that concentration is concentration of sodium hydroxide. But because this is a strong base, and we can also describe this as being monobasic. Now, technically, monobasic actually means the same as monoprotic. It means reacts with 1 mole of base. It means an acid that reacts with 1 mole of base can donate 1 H+. But we can describe this as being a monobasic base. It's a slightly skew-with way of explaining it, but it just means that we've got an OH- that can accept 1 H+. So this 0.1 mole per decimeter cubed, being the concentration of sodium hydroxide, well, is actually going to be the concentration of OH- as well. So we've got the concentration of OH-, but we need the concentration of H+. Well, luckily we have an expression that links those two, that Kw is the concentration of H+ times the concentration of OH-. Well, we know kW. kW is 1 times 10 to the minus 14. And we have got the concentration of OH minus, 0.1. So we rearrange to find H plus. So H plus is kW divided by the concentration of OH minus. Substitute in our values, 1 times 10 to the minus 14 divided by 0.1. And when you put that into a calculator, you get the H plus being 1 times 10 to the minus 13, and that will be moles per decimeter cubed. Now we know that pH, as we've already said, is minus log to the base 10 of the concentration of H plus. So minus log of 1 times 10 to the minus 13 is going to be 13.00, remembering that pH must always be given to 2 decimal places. Now a pH of 13 is much more sensible for a pH of sodium hydroxide compared to the one that we got earlier on. So task 1. I'd like you to, as always, pause the video and calculate the following. 1. The pH of a 1.25 mole per decimeter cube solution of sodium hydroxide. 2. The pH of a 3 mole per decimeter cube solution of calcium hydroxide. And 3. The concentration of a solution of lithium hydroxide with a pH of 13.90. So in each case, think through the data you've been given, think about what you're being asked to do, make sure you focus on the chemicals and give all your answers to 2 decimal places if you're calculating pH. So pause the video and I'll follow with the answers in just a second. So answers for task 1 then. First question was asking you to calculate the pH of a solution of sodium hydroxide with a concentration of 1.25 mole per decimeter cubed. So as before, we've got sodium hydroxide, which is strong and monobasic, so the concentration of NaOH is going to be the same as the concentration of OH minus. It's the first thing you need to think about. We've also been asked to work out pH, and we need to think, okay, pH is minus log to the base 10 of H plus. Now we don't have H plus, but we have got a way of working it out. Now in an exam question, you would normally be told the value of kW. So we take kW. We know that the kW expression is concentration of H plus times concentration of OH minus. We know kW is 1 times 10 to the minus 14, and we've been given the concentration of OH minus because we've been given the concentration of sodium hydroxide. So rearranging, concentration of H plus is kW divided by the concentration of OH minus, 1 times 10 to the minus 14 divided by 1.25, and that gives us a concentration of 8 times 10 to the minus 15 for H plus. And therefore the pH is going to be minus log of the H plus concentration. So minus log 8 times 10 to the minus 15. And when you put that into the calculator, you get an answer of 14.10, again to 2 decimal places. Question number 2, calculate the pH of a solution of calcium hydroxide that has a concentration of 3 mole per decimeter cubed. So again, we want to be working out the pH. We're going to need the concentration of H plus. We're going to need to use kW, which is H plus times OH minus. And so therefore we need to look up the concentration of OH minus. Now, this is calcium hydroxide, CaOH2, and this means that in every calcium hydroxide there are 2 OH minuses. So the concentration of calcium hydroxide is actually going to be times by 2 to give us the concentration of OH minus. So concentration of OH minus is going to be 3 times 2, or 6 moles per decimeter cubed. So that's the concentration of OH minus. We know the concentration of, we know the value of kW, sorry. So we're going to rearrange to find H plus. kW divided by OH minus. 1 times 10 to the minus 14 divided by 6 gives us 1.6 recurring, 1.67 times 10 to the minus 15. And therefore the pH is going to be minus log of H plus minus log 1.67 times 10 to the minus 15. And that gives us a value of 14.78, again to 2 decimal places. And again, that's the right ballpark for a concentration, or sorry, pH of a alkaline solution. Question 3, a little bit different. We're going backwards this time. So this is asking for the concentration of a solution of lithium hydroxide, and we have a pH of 13.9. So we are trying to find concentration of LiOH. That's what we're trying to get to at the end. Now that will be equal to the concentration of OH minus, because it's a 1 OH minus in every LiOH. Now pH we know is minus log of the H plus. So the first thing that we can actually work out here is we can work out the H plus, because H plus is 10 to the minus pH. So 10 to the minus 13.90 gives us a concentration of H plus of 1.26 times 10 to the minus 14. Now looking at Kw, we know that Kw is H plus times OH minus. We've got H plus, we know Kw, so we can now rearrange to work out the concentration of OH minus. Kw divided by the concentration of H plus is 1 times 10 to the minus 14 divided by our value from earlier, 1.26 times 10 to the minus 14. And therefore we get an answer of 0.79 mole per decimeter cubed. So now we're going to move on to look at calculations involving reactions of strong bases. Now, some people find these really difficult, but it is very much linked to the amount of substance topic from year 1 A-level chemistry. And it is really important that when you read through these questions, you don't let the numbers and the wordiness of the questions worry you. Look at the data you've been given. Think about the equations and the expressions that you know linked to moles, concentration, volume, mass, MR and all of that kind of thing, and look for what you've been given and where it appears in those equations. Think like a chemist is something I say a lot, and it is really important to make sure that you don't get blinded by the maths and think through the chemistry that's happening. So at A level, you are expected to be able to work out the pH of solutions for a variety of situations. So you have to look at the solutions of strong acids, something that we've done already. You also have to be able to do solutions of weak acids, that involves Ka. And you have to be able to calculate the solutions of strong bases using Kw, as we've already done in this video. Now the next type of calculation you have to do involves dilution of the above solutions. So you're given a solution of weak acid and told calculate the pH when we add water to it, which is something quite common that we would do. And then you also have to be able to calculate pH of solutions left over after reactions. And the reactions that you need to be able to calculate are for a strong acid plus an excess of a strong base, a weak acid plus an excess of a strong base, a strong base plus an excess of strong acid, and then a strong base plus an excess of a weak acid. Now, these three are going to be mentioned in this video, as are the dilution questions. But strong bases and weak acids are actually to do with something called buffers, and that is a whole section of this topic on its own, so that isn't covered in this video. Now you may have noticed that weak base is not mentioned on this slide, and that's because although you have to be aware of what weak bases are, for UK A-level specifications, so that's not international A-level, but just UK A-level specifications, calculations involving weak bases are not included. So I'm not going to be covering those. So we're going to start off looking at a dilution calculation, and as I said, this is where water is added to a solution. So I've got an example here, a 200 centimetre cube solution of 0.5 molar KOH was made up to 250 centimetres cubed. Calculate the pH of the resulting solution. Now what we've got here is I'm going to do my data and I'm going to highlight using the same colour for the same chemical. So we've got a 200 centimetre cube solution of potassium hydroxide. Now this is just potassium hydroxide on its own. They're asking us to calculate pH, so we're going to be needing to use the normal pH expression, which means that we are going to need to find H+. But we've got a strong base, so this is actually going to give us concentration of OH-. And that should make you think, okay, strong base, I'm going to have to use the Kw expression. And this is something that comes with practice, is recognising strong base is Kw. Now what we've also got is I've got another bit of data here, and I've got here a second volume. So we've got an original volume, and then we have a final volume. Now the concentration that's been given, that concentration is the original concentration. That will only be the concentration of the KOH in the 200 centimetres cubed. And that's because concentration is moles over volume. So the concentration 0.5 will only be the concentration of the KOH in the 200 centimetres cubed. We need to be able to find the concentration of the KOH in the final volume. So if concentration is moles over volume, we want to find the new concentration, or the final concentration. That's going to be the moles of KOH divided by the final volume. So final concentration, new concentration, same thing. Well, the moles of potassium hydroxide is not going to change because this is just in water. The potassium hydroxide is not reacting or interacting with anything. So what we can do, first of all, is we can find the moles of KOH. And that is going to be the original concentration, which we know, times by the original volume, which have also been given. So 0.5 is our original concentration times our original volume, which is 200 centimetres cubed, but we divide that by 1,000 to get it into decimeters cubed. And that gives us moles of 0.1 mole. And that is the moles of KOH. Now, as I've already said, the moles of KOH does not change, but when we add water, the concentration will. So as I've already said, we've got this new concentration that we can calculate using the new volume, which I've highlighted in blue. So we take the moles that we've just calculated, 0.1, and then we divide it by the final volume, which is 0.25. And that is just because 250 centimetres cubed divided by 1,000 is 0.25 decimeters cubed. So our new concentration will be 0.4 moles per decimeter cubed, and that is the concentration in the new volume. Now that's only slightly less than the 0.5 we started with, but we've only added 50 centimetres cubed of water to the original 200, so it won't have changed by that much. Now that we've got this concentration of OH minus, we can use the Kw expression to work out what the concentration of H plus is. So 1 times 10 to the minus 14 divided by 0.4, our new concentration, gives us a concentration sort of equivalent of H plus of 2.5 times 10 to the minus 14, and therefore pH equals minus log to the concentration of H plus minus log 2.5 times 10 to the 14, and we get a pH of, I'll put that in my calculator, 13.6. Again, to 2 decimal places. Now that's quite a lot to think through and quite a lot of maths to be looking at. But it is just a case of thinking about the fact that we've got this original volume and a final volume, and that the concentrations will be matched. Concentration originally will be with the original volume, and the final volume and the final concentration have to go together as well. Now, dilution calculations you approach in the same way for if it's a strong acid or weak acid as well. Just instead of using Kw, to work out H+, if you're doing a weak acid calculation, you would use Ka at that point. And if you were doing dilution of a strong acid, you don't need to do the sort of interim part of that question. You would go straight from working out the new concentration, which would be of H+ over here. So new concentration of H+. You would then use that, taking account of the ratio of the H+'s in your chemical, but you would go straight into the pH calculation. Now the next type of example we're going to look at is strong acid and strong base reaction calculations. This is where we actually put an acid and a base together, and we would get perhaps a neutralization, or more often that we get an excess of one of the chemicals left over. So a 20 centimeter cubed solution of 0.5 molar KOH was reacted with 30 centimeters cubed of 0.2 molar H2SO4. Calculate the pH of the resulting solution. So we're being asked to calculate the pH of what is left over at the end. Okay, so this is the leftovers. And we are either going to have leftover KOH or we're going to have leftover H2SO4. So we have to look at the data of what we've got. We have 20 centimeters cubed of 0.5 molar KOH, and then we have 30 centimeters cubed of 0.2 molar H2SO4, and they react together. Now, to know what is in excess, we have to know how many moles of each react. And we've got here a volume and a concentration of each of these chemicals. And as long as you have a volume and a concentration, you can work out moles. Now always look for where you can work out moles, whether it's mass divided by relative mass or concentration times volume. That's always going to be a helpful thing to do if you get a bit stuck. Work out moles and then think, what can you do with that? So first of all, I'm going to work out moles of the KOH, which is the concentration of KOH times by the volume of KOH. The concentration is 0.5 and the volume is 20 over 1,000. And so we have moles of KOH being 0.01 moles. And I'm going to do the same for the moles of H2SO4. Concentration times volume, 0.2 times 0.03. Now that is just 30 divided by 1,000, 0.03. And so we get 0.006 moles of H2SO4. Now we're looking at an acid-base reaction, so we're actually looking at H plus plus OH minus here. And the moles of H plus is going to be 2 times 0.006 because we have H2SO4. So we have 0.012 moles of H plus. Now if we compare the moles of H plus, which we've just worked out to be 0.012, and the moles of OH minus, what you should hopefully be able to see is that we've got more H plus than we have OH minus. And that means that the acid is in excess. There will be leftover acid. And because the acid is a strong acid, we don't need to use Ka or Kw, we can just use pH equals minus log base 10 H plus. But we need the concentration of H plus and we need the concentration of H plus in the new solution. So first of all, we want to work out moles of H plus in the new solution or the total solution. And that will be how much H plus we started off with, 0.012, minus how much will react. Now, because it's a 1-to-1 ratio, 0.01 moles of OH minus will react with 0.01 moles of H plus, and overall we'll get 0.002 moles of acid left over. Now, as I said, this is quite complicated. This is one of the hardest things. So if you get a bit stuck, just let me know and I can go over it again. But as I said, the moles of H plus that's left over will be the moles of H+ we start with minus how much reacts. And the amount of H+ that will react will be the same as the amount of OH- that we've got present. So we then need the concentration of H+. That will be the moles divided by the new volume. So 0.002 moles divided by the volume, and the volume is going to be 50 centimetres cubed. We've got 30 centimetres cubed being added to 20 centimetres cubed. So we have 50 centimetres cubed divided by 1,000. So 0.02 divided by 0.05 will be 0.04 mole per decimetre cubed, and that's the concentration of the H+. And then we put that straight into our pH expression, minus log of 0.04 gives us a pH of 1.40, again to 2 decimal places. So task 2, take your time. If you need to go back and look over the previous 2 examples, but have a look at these questions and see how you do. For each one, break it down, think about the data that you've been given, think about the equations and expressions, concentration is moles over volume, etc. So calculate the following. Number 1, 100 centimetres cubed of distilled water was added to a 500 centimetre cubed solution of 0.2 molar NaOH. What is the pH of the resulting solution? Number 2, what mass of sodium hydroxide must be added to 250 centimetres cubed in order to produce a solution with a pH of 13.50? And number 3, a 50 centimetre cubed solution of 0.5 mole per decimetre cubed sodium hydroxide was reacted with 50 centimetres cubed of 0.2 molar HCl. Calculate the pH of the resulting solution. As I said, take your time, look at the data you've been given, and see if you can spot where you've got a concentration and a volume of the same substance. Write out the equations and think, what bits of data have you got? Pause the video. If you need to, go back and look at the previous examples, but I'll be going through the answers in just a second. So, question 1. 100 centimetres cubed of distilled water was added to a 500 centimetre cubed solution of 0.2 molar NaOH. What is the pH of the resulting solution? So, this resulting solution is just a strong base on its own, in water, nothing else, no reaction. But what we're doing is we're diluting here. Now we've been given a concentration initially, along with the volume initially, along with the concentration. So that's something really important to look at here. This is our original or initial volume, and we've got here an original or initial concentration. Now we've then been given an additional volume that is being added to it. I'll try and get the colours right here. So we've got here 100 centimetres cubed distilled water is being added. So we have a new volume here, a final volume of 600 centimetres cubed, or 0.6 decimeters cubed. Now, the volume changes, therefore the concentration changes, but the moles will remain constant. So the moles before will equal the moles after dilution. Now, because we've got NaOH, we're going to have to use Kw, because pH we know needs the H+ concentration, and we can't get that directly from the NaOH. So we're going to need to use Kw because it's a strong base, and that's just something, as I've said, that you need to recognise. So taking all that into account, because we've got a volume and a concentration, both initially of the same chemical, we can work out the moles. Now, as I said, it's not a reaction. The moles are not going to change. So the moles is going to be original concentration times the original moles. Volume, sorry. So the original concentration is 0.2 and the original volume is 0.5. 500 divided by 1000 to get it in decimeters cubed. Don't need the negative there. Apologies for that. So the number of moles is going to be 0.1, and that's how many moles of NaOH we have. Now we've now got the number of moles and we have a final volume. So that means that we can work out the concentration after dilution, or the final concentration, because that is going to be the number of moles of the substance we have divided by the final volume. Now each time we're keeping the same things together, so original concentration with original volume, final concentration with final volume, and that's really important just to recognise that. Sorry about the wrong thing, apologies. So the number of moles is 0.1. The final volume we already said was 0.6 because it's the 500 we start with plus the 100 that we end up with, and so the final concentration is going to be 0.167 moles per decimeter cubed. 0.1 divided by 0.6. Now that is the concentration of KOH, but because it is K1OH1, there's one of each, that concentration is also going to be the concentration of OH minus. Now we said that we want to work out the pH, and for pH we need the H plus. If we've got OH minus, we are going to need to use the KW expression. So KW is concentration of H plus times concentration of OH minus. We know KW, 1 times 10 to the minus 14, always at standing conditions, unless you're told otherwise. And we've just worked out the concentration of OH minus. So rearranging for H plus, KW divided by OH minus, 1 times 10 to the minus 14, divided by 0.167, and that comes out to be 6 times 10 to the minus 14 moles per decimeter cubed. pH is equal to minus log of H plus, so minus log of 6 times 10 to the minus 14, and that gives us a pH of 13.22. Again, 2 decimal places as always for pH, and 13.2 is a sensible pH for a solution of strong base on its own in water with nothing else interacting with it. Number 2. What mass of sodium hydroxide must be added to 250 centimeters cubed in order to produce a solution with a pH of 13.5? So I didn't do an example of this calculation already, but you approach this in pretty much the exact same way. You're being asked to calculate a mass of sodium hydroxide. Now sodium hydroxide is NaOH, and we want a mass in grams. So you need to think to yourself, what do we know about mass? Mass is equal to moles times mR, okay, or sometimes people remember it as mass equals Mr. Moles. So we are going to need to be looking at moles, and we're going to need to look at mR. We have got here a volume, which would be better if I highlight that. So we've got a volume here, highlight rather than scribble. So, oh, you leave that in red, that's fine. So 250 centimeters cubed is a volume. We'll get there eventually with these colours. So we have a volume, and if we think about expressions that we know, concentration equals moles over volume. So we've got moles just here, we have a volume that we've been given, so there is going to be something that we can do with sort of combining those and using those values. And we've got a solution with a pH of 13.50, and you need to think to yourself, okay, we know that pH equals minus log of H plus concentration. Now the other thing we need to think about is that this is a strong base, on its own, being put in a solution just with water, so there's no reaction, nothing else, which means that we are going to be able to use Kw being H plus times OH minus. So, first of all, they're asking us to work out what mass. We can't use this first equation just yet, because mass is what they're asking us to find. We don't know moles, and we can work out the MR. The MR is 40 of sodium hydroxide, 40 grams per mole, because sodium's 23, plus 16 for oxygen, plus 1 for hydrogen. So we do have the MR, but we can't do anything with that expression just yet. Now, because we haven't worked out moles yet, although we have the volume, we can't work out the concentration. So we can't use either of those expressions. So what can we do? Well, we've been given a pH, and we should know by now that H plus is equal to 10 to the minus pH. So because we have the pH, we can calculate concentration of H plus. So 10 to the minus 13.50 gives us a concentration of H plus of 3.16 times 10 to the minus 4. Apologies, 14, so minus 14 just there. So that's our concentration of H plus. Now, how does that help us with the scribbling that we've done? Well, we've now got concentration of H plus over here, and Kw, we know the value of 1 times 10 to the minus 14. Now, because for this expression, we've now got two things that we can tick off and say we've got those values, we can work out the third one, we can work out OH minus. So that's what I'm going to do next. Concentration of OH minus is going to be Kw divided by H plus concentration, just rearranging the Ka expression there. So 1 times 10 to the minus 14 for Kw divided by 3.16 times 10 to the minus 14 for H plus gives us a concentration of OH minus of 0.316 moles per decimeter cubed. Now, sodium hydroxide is NaOH. There's one OH minus in every NaOH. So the concentration of NaOH is going to be the same as the concentration of OH minus that we've just worked out. So we've now got the concentration of the solution. So looking at this expression up here, we've now got the concentration of NaOH, and we've got the volume, which is 250 centimeters cubed, and that means that we now can work out the moles. So that's the next step. Moles of NaOH is equal to concentration times volume. We've just worked out the concentration, and the volume is 0.25. So that's the 250 centimeters cubed divided by 1,000. So the moles of sodium hydroxide is going to be 0.0791 moles. And everything I'm just doing here is a 3 sig fig just for ease. I am using the numbers in the calculator though at each time for the calculation. So now we can go on to looking at our final bit of the puzzle. The question asks us to work out the mass, and we can work that out because we've now got the moles that we've just worked out, and we know that the MR is 40. So straight into this mass. My pen has stopped working, apologies for that. Then we've got loads of M's. So mass is equal to moles times MR. So the moles that we've just worked out, 0.0791 times 40, which is the relative mass of sodium hydroxide. And when you put that into the calculator, it comes out to be 3.16 grams, again to 3 significant figures. And finally, question number 3. A 50 centimeter cube solution of 0.5 mole per decimeter cubed sodium hydroxide was reacted with 50 centimeters cubed of 0.2 molar HCl. Calculate the pH of the resulting solution. So we've been given a volume and a concentration for sodium hydroxide. So again, I keep getting muddled up with these pen buttons on my computer. So we have a volume and we have a concentration of the sodium hydroxide, and then we have a volume and a concentration of the HCl. Now pH, again we know that pH is minus log of H+, so whatever happens we've got to work out the concentration of H+ at the end. Now that could mean that we need to use Kw if we end up with excess NaOH. It could mean that we just go straight into this expression, pH equals minus log H+, if we get an excess of HCl, but we have to know which one is in excess. Now we've been given volumes and concentration for each of these, and what we need to think about is how are they linked together, and that is moles is equal to concentration times volume. Now the only way to work out if something is in excess is by working out the moles and looking at the molar ratio or the stoichiometric ratio of the equation when they react. Now NaOH and HCl react together in a nice 1-to-1 ratio, and that is something that you do need to know at A level. That equation comes up time and time again. They won't give that to you, you just need to know it. It's used for back titrations and all sorts of things if you go back to year 1. So I'm going to go straight into this and I'm going to calculate the moles of each, and I'm going to work out the moles of the HCl first. Just that's what I wrote down. So concentration times volume, that will be 0.2 times 50 over 1,000. And so the moles of HCl here is 0.01. I'm also going to work out the moles of NaOH, which again is concentration times volume. But this time we have 0.5 moles times the 0.05, which is 50 over 1,000. And so the moles of sodium hydroxide is 0.025. Now we know that we have a 1-to-1 ratio between the two because I just wrote that equation down, which means that H+ and OH- is also a 1-to-1. That's nice and easy. So straight away you should be able to see that we've got 0.01 of acid and 0.025 of the OH-. And in this situation we've got more OH- than we have H+. Therefore the OH- is in excess. And we have leftover sodium hydroxide. Now that leftover NaOH is going to be what we start with, 0.025, minus how much reacts. Now because it's a 1-to-1 ratio, it will be however much acid there is will react with the same amount of OH-. So the 0.01 moles of H+ will react with 0.01 moles of OH- to form 0.01 moles of water, and we get left over 0.015 moles of NaOH unreacted in the solution left at the end. So that's the excess moles of NaOH at the end of this reaction. Now because we end up with this much 0.015 moles of NaOH in solution, we treat this just as strong base in solution. We ignore the fact there's going to be salt there and everything else. This is sodium hydroxide in a neutral solution otherwise, so we just pretend that it's in water, we treat it as if it's in water, and so we're going to need to use Kw. And Kw is going to allow us to work out what the concentration of H+ is. So Kw divided by concentration of OH-, as NaOH is 1 OH- for every NaOH, the concentration of sodium hydroxide is going to be the concentration of OH-. Well, we need to work out that concentration of OH-, nearly forgot to do that, and that's going to be the moles divided by the new volume, or total volume. So 0.015 moles divided by the new volume, which is 50 centimeters cubed plus 50 centimeters cubed, will be 100 centimeters cubed, which is 0.1 decimeter cubed. And so our concentration of OH- in the new solution is 0.15 mole per decimeter cubed. So if I put that over here in the Kw calculation, I'm going to run out of space. I might have to do some deleting. So we end up with an equivalent H+ concentration in our solution of 6.67 times 10 to the minus 14, and therefore the pH, if we put that into the minus log to the base 10 concentration of H+, which I would write down because you should show where you're working, but I'm going to run out of space. So if we put that in, which I've already written up here at the top anyway, if we put that into our calculator, we come out with a pH of 13.17 to 2 decimal places. Now they are quite involved calculations, as I've said already, but it is a case of going through, looking at the data you've been given and thinking about all of those equations that you're aware of. Those equations that we used extensively last year, okay, the moles is concentration times volume, mass is moles times relative mass, those kind of things. If you can remember those equations and write them down, and then it's a case of what data have I been given, what have I got in my expression, and what can I rearrange to find out. If any of that has confused you, go back and re-watch any bit that you found really hard, and if you need to, get in contact with me. Just send me a message.